Hello, I'm Linda Collins of New York University, and it's a pleasure to welcome you back to the Coursera course, The Multi-Phase Optimization Strategy Most from a Methodological Perspective. This is Module 2, the Factorial Optimization Trial and the Factorial Analysis of Variance, ANOVA. We are beginning Lesson 4, Fundamental Differences between the ERCT and the Factorial Experiment. In the previous lesson, you learned how to describe the factorial experiment and what it is intended to estimate, namely main effects and interactions. In this lesson, you will learn how to express the fundamental differences between the logical underpinnings of an ERCT and those of a factorial experiment, and to explain why the factorial experiment usually requires many fewer participants than alternative experimental designs for examining individual component effects. Let's return to our hypothetical example where we are developing an intervention aimed at reducing viral load among HIV-positive individuals who drink heavily. For the time being, we are supposing there are only 4 candidate components, all with levels no or yes: motivational interviewing, peer mentoring, text message support, and mindfulness meditation. Let's consider some different ways of experimentally examining the performance of these 4 components. The first option we will consider is the one many intervention scientists would go to first: 4 individual treatment control experiments. As we have illustrated here, one experiment would compare motivational interviewing to a control, another would compare peer mentoring to a control, and so on. We are going to compare several different approaches, so let's note some features of this approach. The individual experiments approach requires 8 experimental conditions, that is, 4 experiments with 2 conditions each. To maintain power of at least 80%, based on a standardized effect size of 0.3, would require a sample size of 352 for each of the 4 experiments, for a total required sample size of 1,408. This approach does not enable estimation of interactions. Now let's consider another approach. We will call this the comparative treatment experiment. There are other very similar experimental designs, such as the dismantling experiment, that have identical statistical properties. In a comparative treatment experiment, each of the components under consideration would be represented by an experimental condition in which that component is set to yes and all the others are set to no. There is a condition corresponding to each component plus a control condition in which all the components are set to no. For example, to estimate the effect of motivational interviewing, you would compare the mean of the experimental condition in which motivational interviewing is set to yes to the mean of the control condition. Note that the comparative treatment experiment and other similar experiments are in the ERCT family. This experiment is essentially a 5-arm ERCT. The comparative treatment experiment would require 5 experimental conditions in our example. To achieve a power of at least 0.8, you would need 880 participants. This is a considerable savings over the individual experiments approach. You still cannot estimate interactions between components, though. The third alternative we will consider is a 2 to the 4th factorial experiment. This will have 2 to the 4th, or 16, experimental conditions. For the rest of this course, we will often use abbreviations for the factor names on tables. Watch for this on the next slide. This table shows the experimental conditions in a factorial experiment with 4 factors: motivational interviewing, MI, peer mentoring, peer, text message support, text, and mindfulness meditation, mind. You can see that each factor is set to yes 8 times and no 8 times. Now let's compare the factorial design to the other 2 approaches. The factorial design requires by far the largest number of experimental conditions, 16 as opposed to 8 for the individual experiments approach and 5 for the comparative treatment experiment. However, The factorial design requires many fewer participants, only 352 as opposed to 880 for the comparative treatment approach and 1,408 for the individual experiments approach. If you have been trained primarily in the ERCT, this may be counterintuitive. Let's consider why it is that the factorial experiment often makes very efficient use of experimental participants. Let's start by considering a fundamental conceptual difference between the ERCT and the factorial experiment. First, note that design options A and B are essentially ERCTs. The comparative treatment experiment is a multi-arm ERCT. In our example, it's a 5-arm ERCT. The purpose of the ERCT is direct comparison of individual experimental condition means. In a typical 2-arm ERCT conducted to evaluate an intervention, the purpose is direct comparison of the mean of the intervention condition against the mean of the control condition. You can see that in design option A, the individual experiments approach, the effect of motivational interviewing is defined as the mean of a condition in which motivational interviewing is set to yes and everything else is set to no, versus the mean of a condition in which everything is set to no. Let's look at this within the context of the factorial experiment. Design option A is the equivalent of pulling out experimental condition 9, which is darkly shaded, and experimental condition 1, lightly shaded, and comparing their means. This kind of effect is often called a simple effect in the social and behavioral sciences and is more widely known as a conditional effect. Design option B, the comparative treatment experiment, defines the effect of motivational interviewing in the same manner as design option A. Again, this is the equivalent of comparing the means of conditions 9 and 1 in the factorial experiment. But as we have discussed, a factorial experiment defines the effect of a component differently. In a factorial experiment, the effect of a factor is its main effect. The factor also exerts an effect through any interactions it may have with other factors. We will discuss interactions at length in future lessons. The main effect of MI is the mean of conditions 9 through 16 minus the mean of conditions 1 through 8. We said we were going to discuss why it is that, as compared to the individual experiments and comparative treatment approaches, the factorial experiment requires many fewer participants to maintain the same level of power. Let's consider what happens when we estimate the main effect of peer mentoring. The main effect of peer mentoring is defined as the mean of the conditions in which the peer mentoring factor is set to yes, that is, conditions 5 through 8 and 13 through 16, minus the mean of the conditions in which the peer mentoring factor is set to no, that is, conditions 1 through 4 and 9 through 12. Notice that this estimate of the main effect of the peer mentoring factor is based on all of the experimental conditions and, by extension, all of the participants. It's based on the same participants that were used to estimate the main effect of motivational interviewing. They're just rearranged. Some of the participants who were in the no level of motivational interviewing are in the yes level of peer mentoring, and vice versa. Similarly, the main effect of the text message support factor is defined as the mean of the conditions in which text message support is set to yes. This is conditions 3, 4, 7, 8, 11, 12, 15, and 16, minus the mean of the conditions in which text message support is set to no, that is, the remaining conditions. And the main effect of the mindfulness meditation factor is defined as the mean of the even-numbered conditions minus the mean of the odd-numbered conditions. Notice that in these definitions, all of the experimental conditions are involved. They are just combined in different ways to define the different effects. In my opinion, this is the genius of the factorial analysis of variance. In a factorial analysis of variance of data from a 2 to the k experiment using effect coding, that is -1, 1 coding, we're going to come back to that, each main effect and interaction effect estimate is based on all participants. In a sense, experimental participants are recycled. By this I mean each participant is used in multiple effect estimates. Yet, under many circumstances, the effect estimates are uncorrelated. We will discuss this later. At this point in the process of learning about the factorial experiment, you may be mulling over how you feel about defining the main effect as an average across many experimental conditions. I want to share a quote from Fisher about this. It's a bit long, but I love it. Fisher wrote, quote, "Any conclusion has a wider inductive basis when inferred from an experiment in which the quantities of other ingredients have been varied than it would have from any amount of experimentation in which these had been kept strictly constant." The quote continues, "In fact, as the factorial arrangement well illustrates, we may, by deliberately varying in each case some of the conditions of the experiment, achieve a wider inductive basis for our conclusions without in any degree impairing their precision." End quote. What Fisher is saying here is that there are advantages to defining the main effect as an effect that obtains on average across a wide variety of circumstances, rather than as an effect that obtains under very specific circumstances. To me, this means that an effect that obtains on average across a wide variety of circumstances is more likely to remain robust if circumstances change. That's an empirical question, of course, but not one we always have the opportunity to address. Consider how this relates to examination of intervention components. I would argue that it is desirable to define the effect of a component as an average across lots of different combinations of components and component levels. Now, why do I say this? One reason is that the continual optimization principle of most suggests that the intervention will evolve over time. New components will be devised, tested, and added to the intervention, and weak components will be removed. So it makes sense to try to build an intervention out of components with effects that obtain within the context of lots of other components. A second reason is that the intervention we designed is not always the one the participants complete. Participants do not always receive or comply with all of the components. The way effects are defined in a factorial experiment has some implications that are worth noting. Whereas the objective of an ERCT is direct comparison of the means of experimental conditions, the purpose of a factorial experiment is not direct comparison of any pair or subset of the experimental conditions. In a factorial experiment, the effect estimates are based, as we illustrated, on the means of combinations of experimental conditions. In particular, in a factorial experiment, the objective is not comparison of any condition or set of conditions to a single experimental condition that is designated as the control. This means that although condition 1 looks like a traditional control condition, it does not serve as the control in the illustrated factorial design. We will discuss this at length later. Let's review some fundamental differences between the ERCT and the factorial experiment. The ERCT was designed for direct comparison of a relatively small number of experimental conditions, whereas the factorial experiment was designed for estimation of the main effect of each factor and interactions involving two or more factors. In the ERCT, effects are estimated via direct comparison of individual experimental conditions. By contrast, in the factorial experiment, effects are estimated via construction of combinations of experimental conditions. Finally, in the ERCT, each participant usually contributes to a single effect estimate, but in the factorial experiment, each participant contributes to multiple effect estimates. In this lesson, you learned how to express some fundamental differences between the logical underpinnings of an ERCT and those of a factorial experiment, and to explain why the factorial experiment usually requires many fewer participants than alternative experimental designs for examining individual component effects. In the next lesson, you will learn how to express the factorial ANOVA as a regression equation, code main effects and interactions using effect, that is, -1, 1 coding, and explain the concept of balance in factorial experiments. Here is the reference cited in this lesson. See you next time.